In this video, we're going to look at an example with Newton's second law that involves two blocks touching each other in a surface with friction. So basically, we're going to say that the mass of this block is m1 and the mass of this block is m2. And we're going to say we have a horizontal force acting on block 1. We're going to call this force F. And since we're dealing with a surface with friction, we're going to say that when this force acts, that the blocks do move, and so we have kinetic friction. We're going to say that the coefficient of kinetic friction is just mu k. So this is basically the four things that we're given, right? So we're given F, m1, m2, and mu k. These are the four things that we're given. And so basically what we want to do is we want to find, all right, first thing, of course, usually in most problems like this, what's the acceleration of the system, right? All right, so find the acceleration of this system. So how would we do that? Well, basically what we have to do is we have to think about pretty much the forces acting on both of our blocks. So we're going to draw free body diagrams for both block 1 and block 2, right? So for block 1 and for block 2. All right, so the idea is, remember, we're dealing with a case where the two blocks are touching each other. So when this force acts on block 1, well, block 1 is going to push on block 2, right? Block 1 is going to push on block 2 and exerts a force on block 2 going that way. Now, if block 1 pushes on block 2 will push back on block 1 with that same magnitude of force, right? This is just a case of Newton's third law. And so basically they have the same magnitude of force, so we're going to label them both as F sub c, meaning contact force. And even though they're technically not the same force, right, they have the same magnitude, so we're just going to label them like that. Okay, so basically block 1 pushes on block 2 with this force, block 2 pushes back on block 1 with that same magnitude of force. And that's the idea of problems like this. So we see that for block 1, right, thinking about the forces acting on block 1, we know that we have a horizontal force, F, acting to the right on block 1. So we have F to the right. And we also, as we just established, we have a contact force, right, block 2 pushing on block 1, right? This force to the left. Right, so that'll be FC. And also we're dealing with friction, right? And so when this force acts, the blocks are going to move this way, meaning friction will act to the left, right? And so this right here would be the kinetic friction on block 1. So we're going to call that F1K, right? All right, also block 1 has a weight force downward, of course, right? And since block 1 is on a surface, has a normal force upward. So we're going to say this is just F1N, right? Normal force of block 1. So that's basically the forces acting on block 1. Now for block 2, right? Notice how we have the contact force, right? FC acting to the right. It's block 1 pushing on block 2. So FC goes to the right. Right? Also, by the way, this force, it only acts on block 1, right? Right? So it's not acting on block 2. So we don't include this force for block 2, right? Also, friction, right? Right? Remember, system moves this way, friction acts this way. So the friction on block 2 will point to the left, right? So this right here, F2K, right? Kinetic friction for block 2. Of course, block 2 has a weight force downward, so we're going to call this M2G. And also, since block 2 is on a surface, normal force upward. This is what we'll call F2N. And this right here is basically the forces acting on both of our blocks. So now, in order to find acceleration, we got to know net force statements for both of our blocks. Basically, that's usually what we do with these problems. We write net force statements for both of these blocks. And what we want to do is we want to write net force statements involving the acceleration. So pretty much what we're going to do is we're not going to involve our normal force or weight force because normal force and weight force cancel out, don't they? And so acceleration only occurs in the horizontal direction. So in our net force statements, we're only going to worry about these three for block 1 and these two for block 2. right? Because normal force and weight force, they cancel out, right? Only movement in the x direction. So, as for the net force statement for block 1, really it's just F minus Fc minus F1k, right? And by the way, acceleration is to the right, so we're going to say right is our positive direction. So that's why we're saying it's F minus Fc minus F1k. Also, net force on block 2, really Fc minus F2k. Okay, so now what we have to do is we have to continue rewriting our net force equations in terms of as much stuff that we know, right? We know that net force is just mass times acceleration, so we're just gonna write this as m1a is equal to, right, F minus Fc, and we know what kinetic friction is, right? If we recall, kinetic friction is just mu k Fn. And so we're just going to apply that idea to what we're doing right here. So really, F1k is just mu k F1n, right? Normal force block 1. Right? Right? And, right, continuing further with this. We know what normal force is, right? We know what it is because normal force and weight force cancel out, which means that the normal force and the weight force must be equal to each other. So, basically that means F1n is equal to m1g, right? That's the whole idea. And also same thing here, right? F2n will equal m2g. So, I'm just gonna write that right here. F2n would have to equal m2g, right? Because they cancel out, right? No movement in the y direction, right? System only moves in the x direction, so that's the idea. Okay. Mu k and F1n is just m1g, so we get m1g. And that's basically as far as we can write this net force equation. You can't really write it down any further. All right, so moving on to our next one, right? Net force is just m2a, right? And we know what kinetic friction is, as we just established right here. Well, my bad, minus, right? F2k is just gonna be mu k F2n. Right, and we can keep going, right, because we know F2n is just m2g. And that's basically as far as we can go for both of our net force equations. Basically, we have two equations and two unknowns, right? We don't know the acceleration, and we don't know the contact force, right? We don't know the acceleration, we don't know the contact force. So really, we have a system of equations here, where we have two unknowns. So how do we actually solve the system of equations? Well, we could solve for one of our variables. For instance, we could solve for the contact force here, and then substitute that into contact force of this equation, then solve for acceleration, right? We do substitution, but it turns out it actually makes it quite nice for us if we just add our equations, right? If we add this equation to this equation, because what's going to happen is contact force will cancel out, and we can solve for acceleration, right? So we're just gonna rewrite this equation right here, right? M1a equals F minus Fc minus mu k m1g, and we're gonna add it to this equation. So we're gonna add m2a, right, equals Fc minus mu k m2g. So basically, this is what we're doing. We're adding these equations together. And notice how the whole idea of what we're doing here is contact force cancels out, and we can solve, basically, we can solve for acceleration now. Right? So, adding the left side of the equation, we get m1a plus m2a. And for the right side of the equation, we get F minus mu k m1g minus mu k m2g. Right? This is basically what we have for adding left side of the equation, adding right side of the equation. Right? And notice how we can factor out the acceleration, because we're going to need to solve for acceleration, so let's just factor out acceleration here. And on this side, right, notice how we could factor out mu kg, right? we're going to factor out a minus mu kg. So minus mu kg. And so what we're going to get inside is m1 plus m2. Right? So this makes it look simpler, a little bit simpler to look at. And so we can now just solve for acceleration. And so when we solve for acceleration, we get f minus mu kg times m1 plus m2 all over m1 plus m2. And so this right here is the acceleration of the system. And so yeah, that's basically the idea. And so we've solved for the acceleration of the system, but now that we've solved for the acceleration of the system, we could also find the contact force, couldn't we? Right, so we can also find the contact force. So in order to do that, we're going to erase what we have here, but I'm going to rewrite this right here because we need this. So I'm just going to write this at the bottom, right? Acceleration is f minus mu kg times m1 plus m2. Right, I'm just going to box that in, saying it's our final answer for acceleration. Okay, because using that, we can find the contact force. So I'm just going to erase this because we don't really need that anymore. Right, we just go back to our original two equations right here. We can use either one. We substitute acceleration to either one of these equations to solve for the contact force. Right? So this equation looks a little bit easier to look at, doesn't it? Right? And so using this equation, solving for contact force, if we were to solve for FC, FC is really just m2a plus mu k m2g. And we could make this easier to look at by factoring out m2. All right, so we get m2 times a plus mu kg, and all we got to do now is substitute what we have for acceleration into what we have right here, right? So FC is m2 times what we have right here. So f minus mu kg times m1 plus m2 all over m1 plus m2, right? This right here is the acceleration, and we just add mu kg. Right, so this is basically what we have. But this is actually really cool, because what we can actually do is, what we're going to do is we're going to add these together into one fraction, and we got to get the same denominator, right? So basically, what that means is we got to multiply mu kg, right? We got to multiply mu kg. We got to multiply by m1 plus m2, and then divide by m1 plus m2. So now we can combine these together into one fraction, right? And notice what happens when we do that, right? This is actually really cool. Clearly, we're going to have the same denominator, right? So we get m1 plus m2. Right here we have f minus mu k g times m1 plus m2, and then we're just adding mu kg times m1 plus m2, right? So add mu kg times m1 plus m2. And so notice what happens. We get this, and this to cancel out. Because minus this plus this is the same thing, right? They cancel out. It's all gone. Turns out the coefficient of kinetic friction doesn't matter. And we get that the contact force is equal to m2 over m1 plus m2 f. And this is in fact the same result that you would get for the contact force if there wasn't friction. If this was a frictionless surface, then you would still get this result. And it makes sense because this doesn't matter, right? It doesn't matter what the coefficient of kinetic friction is. And so this right here is basically the idea. And so basically, if you were to have given a problem where it involves contact, it pretty much involves two blocks touching each other and a surface with friction, well, the idea is they'll usually ask you the acceleration of the system and the contact force between the blocks. And so this is basically the idea of how it all works. And so that's pretty much it.